mathematics. How do you know whether a function that is undefined at x equals c is a whole or an asymptote? Because it's one of the two. It's not neither, by the way. This is not even an option. Okay. Is it a whole or an asymptote? What people frequently say is that if the indeterminate form is 0 over 0, it's a whole, and if it's a number over 0, it's a vertical asymptote. Most of the time that's probably true, but not always. Not always. If the form is indeterminate, if it's 0 over 0, that does not guarantee that it's a whole. It really, what it says is it's one of the two, and you have to resolve the indeterminacy before you know which one. Okay. When I resolve the indeterminacy, if I get a number, that's where there's no 0 on the bottom, then it's a whole. And the limit is telling me the value of the function at that whole. That's what we've always seen in the past when we've done problems like this. You get what I mean? Like, we starts off 0 over 0. So we factor the top and the bottom, and we cancel some factors, and we get an answer, right? What did that mean? That meant it was a whole. The function didn't exist there, but it had a limit that ants were approaching from both sides, which was the value of the function at the whole. Give me 1 to 5 so far. Is that all making sense? Okay, we've seen stuff like that. Or we've seen stuff like we immediately get a number over 0, and it's DNE. And now we know it's a vertical asymptote now, right? Okay, but it doesn't always work that if it starts off as 0 over 0, it ends up being a whole. Let's look at 2 examples. How about the blue function here? If we take a limit of this function, as x approaches 2, we get 0 over 0, right? So what do? We factor the top, correct? Okay, what does the top factor into? Okay, x minus 2 times x minus 2. So the quantity x minus 2 squared over x minus 2 as x approaches 2. Well, we can simplify that. What is x minus 2 quantity squared divided by x minus 2? Algebraically. X minus 2, okay? Well, that's just 0, right? So we got an answer, right? What does that tell us? Then what was going on in our original function at 2? Okay, it was 0 over 0, but we did more work as required, and we got an answer of 0. The limit of the function is 0. So say it again. No. So then it's a whole. It's a whole if we resolve the indeterminacy and we get an answer, a finite answer, right? So if I were to graph this thing, in fact, let's do that. Let's look at the graph. Let's attach some graphs to this, and you'll see the difference between these 2 functions. So f of x equals x squared minus 4x plus 4 all divided by x minus 2. Okay, I'm going to make this blue so it matches the blue function. And what do we notice here? At x equals 2, if I drag this thing along, what do we see? We get, that's not right. What's going on here? No, that's supposed to say undefined. There it is, right? Okay. So now, this is really tricky here. If I go, let's see if I can, oh, good. I think I captured it. Perfect. All right. So there it is, right? Undefined. Yes. Okay. So that one's undefined. Let's put that picture in there. Okay, so there's the picture that goes with the blue one, right? Undefined. Okay, let's go down, and that's a hole. Clearly, that's a hole in the function, isn't it? Right, that's what I meant to say. It's a hole. The function is undefined at that one spot, but there's just a little hole there that the ants were approaching. Yes, sir. Mm-hmm. If you get so if you have an indeterminate limit and the indeterminate limit, when you resolve the indeterminacy, when you cancel, right, you get a finite answer like zero. Zero is just a number. Then it's a hole. Okay. Okay, so that's what we're going to look at. So now here's part two of our discussion. Let's look at this red function, which is a little different. And let's call this g of x. I called them both f of x. That was dumb. Let's call this g of x. Okay, everybody agree? Again, that's giving me 0 over 0, isn't it? If I try to evaluate this directly. Okay, but when I do more work this time, I get x minus 2 on the top and x minus 2 squared on the bottom. So this time, when I simplify that, when I cancel the x minus 2's on the top and the bottom, I get the limit of 1 over x minus 2 as x approaches 2, which is 1 over 0. Sorry, not infinity. 1 over 0. Okay, what's that mean? No, well, DNE, but that means vertical asymptote, right? Because our rule is if we end up getting a number divided by 0 when we take a limit, that always equates to a vertical asymptote. Now let's look at the difference in the graphs. Yes. Oh, whoops, I got to fix that. Yep. Let me fix that. Okay. So let's fix that. That's supposed to be one of my probably numerous mistakes. See anything else right off the bat and I messed up? Okay, so that gave us 0 over 0, right? Okay, if we look at the graph of the red one now, look what we get. Okay, at x equals 2, we get the vertical line, get the vertical asymptote x equals 2, right? So let's make that red, let's make it dashed. If I turn this guy off, there's example 2. See the difference? That's clearly a vertical asymptote. Okay, so the notes state this correctly then. After removing the indeterminacy, if direct substitution yields a limit of the form a over b, where b is not equal to 0, right? No 0 on the bottom. The function has a hole at c. After removing the indeterminacy, if direct substitution yields a limit of the form something non-zero, right? A non-zero number divided by 0, then the function has a hole. I mean, it has a vertical asymptote, sorry, right? Okay, give me thumbs. Is it a huge deal? I mean, probably not. You're not very seldom. We haven't seen one of these all year until today, right? But just be aware that it can happen. Yep. Yeah. Well, no. The limit exists. Both of those, the function doesn't exist, right? Because in both of those cases, we have to exclude 2 from the domain because it gives us a 0 in the bottom, right? In the first example, the limit did exist and was equal to 0. That's a hole. The second, the limit did not exist. That's a vertical asymptote. Okay? All right. So that just ties up a little hole, excuse the calculus pun there. That fixes the one last unresolved issue we had from 1.2 practice 4. So the next issue that we're going to look at tomorrow, I just want to introduce something to you today. Is I guess we don't probably need this problem. I mean, we know what to do here now, right? We would just find the values of x that are zeros of the denominator. If we end up with a number divided by 0, it's a vertical asymptote, end of story. If it's indeterminate, we got to do more work. It could be either. If we resolve the indeterminacy and we get a finite answer, it's a hole. If we resolve the indeterminacy and we get a number divided by 0, it's a vertical asymptote. Okay? You had a question? Okay. All right. That was the best kind. Okay. So then we've encountered vertical asymptotes when we evaluate limits and end up with the result, a number divided by 0. How could we locate a function's horizontal asymptotes? Because that's our next goal, right? We just dealt with vertical asymptotes. How are we going to find horizontal asymptotes? Do you have a suggestion? So I see what you're saying. You were thinking of this like looking at it like an inverse, flipping the x and the y and treating. You probably could do something like that. It'd be very difficult, but it's a creative way to look at this problem. It's not going to be the recommended way. That would end up being very difficult in many cases, if not impossible in many cases. But it was a good idea. So that's what we're going to talk about tomorrow is how we do this. Before we jump into that, there are some key differences between horizontal asymptotes and vertical asymptotes. So you cannot cross a vertical asymptote. When we get into the part of the class where we look at some functional analysis, we're going to take a function and I'm going to show you guys how to build, and this is really cool. And this is kind of my own deal. I'm very proud of this. Show you guys how to build a little table that will allow you to really quickly analyze the function for all of its important characteristics, minima and maxima, points of inflection, asymptotes, symmetry, all that stuff. We're going to find that when we have vertical asymptotes, it's like creating separate little parts of the domain that almost act like their own little universes, right? An ant walking along the function can never cross that vertical asymptote. So the ant is going to be partitioned into either the part to the left of a vertical asymptote or the part to the right. They can never cross it, right? So you can't ever cross a vertical asymptote. You can cross a horizontal asymptote. It's no big deal. Horizontal asymptotes work very differently. Here's an example. So the definition of a horizontal asymptote is going to be the horizontal line y equals L if one of these two things or both of these two things happen at the same time. The limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity equals L. So the concept here is if we want to find horizontal asymptotes, we have to explore the behavior of the function way out at its infinite tails, way out infinitely far to the right or infinitely far to the left. if the behavior becomes consistent and the behavior of the function is that it more and more closely approaches a specific y value, the further I go to the left, to the right, or the left, then that constitutes a horizontal asymptote. What is a horizontal asymptote? It's just a line that the function tends to stick to as you get closer and closer to infinity or negative infinity. For a vertical asymptote, what did that mean? If we go back for a second and look at our graph that we built here, what was that vertical asymptote? It just meant as the ant approached the value of 2 from the left, what happened? The behavior of the function was such that it more and more closely stuck to that vertical line. It never gets to it, but more and more closely it mirrors that line the closer we get to 2 from the left or the right. Anybody see that? Yep. Uh, there is. Yeah, there is a horizontal asymptote here at 0. You're right. If we were to go further out there, yeah. Mhm. No, in this case it wouldn't. You're right. But in many cases it can. So this is our definition of a horizontal asymptote. Let's look at an example. What if we take the function f of x equals sine x over x? If I graph that function, and we'll explore functions like this tomorrow in more detail, or maybe the day after. Look what happens. This function crosses through the x-axis an infinite number of times, right? But wouldn't you agree that the wave train is getting damped to the right and the left the further I go in those directions? The oscillations are getting smaller and smaller and smaller. And if I were to go way out there, what you'd find is that trend continues. And so even though the function is oscillating around a whole bunch and passing through the x-axis an infinite number of times, the trend is that it's always getting closer and closer and closer to the x-axis, right? And so even in this weird case, we would say, yeah, there is a horizontal asymptote that guides the behavior of the function. Infinitely far to the right, which we can never get to, we should expect that if we go infinitely far, we're going to end up at the x-axis. Now that's a weird concept. We say if we, at infinity, we say this all the time in physics too. At infinity, the y value would be 0. Okay, well, can you get to infinity? No, but you see the idea, right? It's illustrating the trend that we always, this continuous trend that we have as we move further and further to the right or the left. Okay, so give me 1 to 5. Do you get you just understand what we mean in this case? How we could say that this function has a horizontal asymptote. Does that part all make sense? Okay, questions. If you can ask a clarifying question, that would be great. Yes, sir.
This is just another question, but are vertical asymptotes like used in like physics?
Absolutely. Yeah. Like if you, an example would be all the time. Like if you were going to, well, the fundamental problem with modern physics is that we can't reconcile general relativity, which is Einstein's baby. That's the our understanding of gravity, which is that massive objects warp the space-time continuum, and that's what causes gravity, right? With quantum mechanics, you can get down to these infinitely small scales. If you were to go down to an infinitely small distance in general relativity, you would end up with this infinite density in a black hole, for example, or at the beginning of the universe in the Big Bang, you'd end up with an infinite density, and you can't have infinities in nature. It's impossible. And so, yeah, you get this. If you look at this from a general relativistic perspective, you get a vertical asymptote when you shrink an object down into a black hole, when its size becomes infinitely small, but its mass remains finite. You get these. That is an example of a vertical asymptote. Yeah. So you do see them. Yes. Any other clarifying questions on that? Okay. So then what's helpful to do here, okay, one other thing. So limits at infinity. I'll throw out this theorem. If r is a positive rational number, and by the way, we can show that this works. I probably won't do this proof just because we don't have time to do it, but we could show that this works if r is any positive real number. Doesn't even have to be a rational number. We could prove that it works for all real numbers, even irrational numbers. then the limit of some constant divided by x to the r as x approaches infinity is 0. Okay? And the limit of c divided by x to the r as x approaches negative infinity is also 0. Okay, why is that? Think about it this way. Think about the behavior of a function, right? What's a bigger fraction? When I said function, I meant fraction. Think about the behavior of fractions. What's a bigger fraction? 1/10 or 1/100th? 1/10, right? If the top of a fraction stays finite and the bottom of a fraction increases, isn't that driving the value of the fraction smaller and smaller and smaller, right? So in a case like this, then, if we're taking a limit where the top is staying constant and on the bottom I've got x to the r where x is approaching infinity, isn't the bottom of the fraction going to be carried to infinity then? What's the logical limit of that? If the top is staying at some constant value and the bottom is approaching infinity, what value is the fraction itself approaching? It's got to be 0, doesn't it? Right? So it really, you can pretty easily reconcile that if you think about it. You wouldn't. R could be 1. Right. But this is saying you can even be more general than that. You can say we can make the more general, the better the theorem, right? So for example, if we took the limit of this function as x approached infinity, what's the answer going to be? It's going to be 5, isn't it, right? As x approaches infinity, isn't this term right here going to approach 0? I'm going to end up with 3 over an infinitely large number, which is 0, effectively 0, right? So we get the answer 5. So that's this doesn't seem like much, but this is the theorem that we're going to appeal to tomorrow when we prove a bunch of different shortcuts for evaluating limits of rational functions. It's no big deal. You'll see that tomorrow. You guys will come up with the proofs yourself. I'll just write them down and we'll be able to look at any rational function and by inspection, without even doing any, at the end of the day tomorrow, without even doing any algebra, you guys will be able to tell me, okay, the limit of that one is 0. The limit of that one doesn't have a limit, does not exist. The limit of that one is this number. And there's 3 possibilities. You'll all be able to pick that out tomorrow. Okay, to get there though, I want to take you on a little tour of a function, and I want to point out a really important concept. And this is all I'm going to do today. So let's look at this function. Here's my function. It's this polynomial. It's got some coefficient of x to the 4th plus some coefficient of x cubed plus some coefficient of x squared plus x. Okay, and we're going to look at this thing on different scales. Well, right now, which of those 4 terms appears to dominate the behavior of that function? The linear, the quadratic, the cubic, or the quartic? Everybody agree the linear one does? If I superimpose our polynomial with the graph of y equals x, well, they line right up, don't they? So it would appear on this scale, if we were going to employ inductive thinking reasoning instead of deductive reasoning, we would say, okay, well then clearly the dominant term in that polynomial must be the linear one, but it's not. I mean, if I zoom out a little bit, pretty quickly we can see that things change in a way that makes it nonlinear. Okay, now it's nonlinear, right? If I compare that to a quadratic function, they seem similar, right? So we might say, okay, well, it's the quadratic term that dominates. Of course, if I go out a little further, I see that no, that's not the case. It's not the quadratic term. It seems to be the cubic term. It matches most closely. And obviously, if I go out even further, there's going to be a point where all those other terms are not going to matter, and only the quartic term is going to be the dominant term, right? And if I go out far enough, I got to go ways, but if I go out far enough, and I just need to tweak this a little bit. Let's see. What if we let x-axis go from okay, let's just try zooming out from there. Oh, by the way, so I'm only graphing the blue function. the polynomial. Got to go out a ways, quite a ways. Maybe I was a little too aggressive with that, but okay, there we go. Now, do you even see that looks pretty quartic, doesn't it? If I look at that compared to a quartic function, they almost line up perfectly. Do you see any linear nature to that or quadratic or cubic? You don't at all. The point is that if our input values are big enough and we're dealing with a polynomial, all of the terms other than the leading term, the dominant term, become utterly insignificant. And if we're going to take the limit as we approach infinity or negative infinity, all we have to consider is that leading term. Everything else just is background noise. Okay? All right. See you tomorrow. All right, so today we are going to look at stuff we started yesterday. So limits at infinity is the topic. So this is what this is going to guide us to understanding is the end behavior of functions. Right? So we looked at this theorem yesterday. We just said that if we have a constant divided by x to any power in the limit that x approaches either positive or negative infinity, that fraction is driven to zero in the limit because the bottom is exploding and the top of the fraction is remaining constant, right? Okay, so our goal then is, can we resolve this limit? Okay. The limit of this rational function, 2x plus 5 over 3x squared plus 1. Okay, so I want you everybody to click and close, and this is one I got to have everybody completely focusing on because this is a pretty big deal. You're going to use this a lot. So what could I do here? Right now, if I try to plug in infinity, I get infinity over infinity, which is indeterminate. Okay, that's another species of indeterminate limit. We got to do some more work on this. Okay, any ideas? A couple ways we could go about this. Yeah, Jonathan.
This is just probably just the first step. It doesn't really do anything, but we could probably just have two different problems. You'll have the limit of x minus infinity and then the equation and then limit as x approaches a
Pause.
positive.
Okay, I mean you could break it into separate limits. You could. You absolutely could. What we're going to find here, which is kind of nice, is that for rational functions, one thing we're going to find is it doesn't matter. We should get the same result in either direction. If we approach positive or negative infinity, we should always get the same result for our rational function. Okay. Well, I'll qualify that a little bit when we're done. But how am I going to solve that indeterminate? Yeah, I could factor. What could I factor out maybe of both of those? I'd like to take advantage of this theorem if I could. Idea? Go ahead.
Let's see. Probably, so we split the entire equation, so you'll have 2x over 1 and 5 over 3x squared.
Can't do that. I can't just arbitrarily split it up like that. I've got this common denominator that I can't split. Okay. But is there something I could factor out of the top and bottom? And really, there's two ways we could go. They both would work. Get an idea, Julian? An x plus, I can't factor out an x plus 1 out of either one of those. Okay, and I'll give you a hint. You don't have to factor anything. This isn't some kind of fancy, I mean, we're just trying to factor out maybe just a common factor. Okay, we could take out an x. What if we factored out an x? Let's see what happens. Oh. If I take an x out of the top, what's left behind? 2 plus, if I factor something out, I'm dividing it away from both terms, right? Factor it out means to undistribute it, to unmultiply it, which is to divide it, right? 5 over x. Everybody get that? Okay. Really what we did, if I want to factor an x out, is I took each of these two terms and I divided by x to see what remains. 2x divided by x is 2. 5 divided by x is 5 divided by x. Can't simplify that, right? Okay, what about the bottom if I factor an x out? What am I going to get there? 3x plus 1 over x. Okay. All right. So that's helpful. And look what happens now. We get some cancellation, don't we? Right? That cancellation is key. The x's cancel. And now if I apply this theorem up here, if I take the limit as x approaches plus or minus infinity, what's going to happen to each of those terms that has a constant on the top and an x on the bottom? They're going to go to 0, aren't they? Based on this theorem up here, that is going to 0 and that is going to 0, right? Okay, give me thumbs on that. Does that make sense? Okay. So then this becomes the limit of 2 over 3x as x approaches plus or minus infinity. Well, what's that going to be? 0, isn't it? Because I've got a constant on the top and I've got a power of x on the bottom. I think it's a little bit easier proof to see if you just make one little change here. What if we factor an x squared out of the top and the bottom? And the motivation for that is that's the biggest power of x that ever shows up. If I factor an x squared out of each top and bottom, wouldn't I just get a 2 over x plus 5 over x squared remaining divided by 3 plus 1 over x squared? Those guys cancel. And now look, every term up there except the 3 is driven to 0 in my limit, right? 0, 0, 0. Okay, make sense? Okay, I've even got a better way to do this though. Based on our discussion yesterday, if I were to, I just thought of a good way to maybe show this. Okay. Yes. Oh, those are mine. Awesome. Thank you very much. Nice. Awesome. Thank you. So we said that when we look at any polynomial, and a rational function is a ratio of polynomials, right? That in the limits that we go infinitely far in the positive or negative direction, what happened? Right? We ended up with this polynomial, this quartic polynomial. And if I went really far away from the origin, really large values of x, wasn't the only term that really mattered that dominant term, that first term, the x to the fourth power. Everything else was just background noise, right? So this is kind of tricky, but this is a really cool way to do it, I think. This is equal to then, as long as we're taking the limit as x is approaching plus or minus infinity, this is exactly equal to the limit of 2x over 3x squared, right? Because only the dominant term on the top and the bottom is going to ever make any difference, right? Would you agree with that, everybody? Right? And so I can ignore all these other lower terms, and I'm just looking at the ratio of 2x over 3x squared. Well, now because we only have a single term, these are just power functions on the top and the bottom. I don't have any other terms. I can easily simplify this quotient, right? This just becomes the limit of, I could cancel an x on the top and bottom, and I get 2 over 3x as x approaches plus or minus infinity, which is obviously 0, right? Because the bottom is exploding and the top is not. Okay? Everybody get that? That's the easiest way to do it, right? Is you just take the limit of just the terms that are going to infinity the fastest. So if we wanted to discuss this in a different way, I mean, algebraically, this is the stuff you have to show, but conceptually, we could probably even, yeah, question?
I think the only thing that I don't get is how the x's appear. When you factor out the x's, you get the 5/x.
Mm-hmm.
And that's the part. That's the only part that I don't get.
Okay, so how do we get that? So the way we get this term right here is we're going to take 2x and we're factoring out an x. So 2x over x gives us 2. Okay, to get this one, we're taking these different color. We're using the 5 and we're dividing by x. So 5 over x doesn't simplify; it just gives us 5 over x. Right? When I'm factoring something out, I'm undistributing it, which means I have to divide it away what I started with there, right? And we can prove it by just reversing the process. If I distribute this x, sure enough, I'm going to get my 2x, and x times 5 over x is going to cancel that x on the bottom, and I just get my 5, right?
So is there like always an imaginary x?
No, there's not. But if I'm gonna factor an x out, then what's left behind after I factor that x out is what I get when I divide my original term by the thing that I'm factoring out, right? So 2x, when I factor the x out from this first term, well, 2x divided by x simplifies just to 2. We don't normally do this, do we? Right? We don't normally factor things out that are going to cause us to have a fraction, but we could if we wanted to, right? Factoring is a process of division. When I factor something out, I am dividing the function I started with by the thing that is being factored. Okay? Does that make sense? Okay. Other questions? On the bottom one? Okay, this goes back to that discussion yesterday where we zoomed out. If we have a polynomial, here, I'm just going to go back to that real quick. Does that make sense? It makes okay. So right. So if I zoom way out, all those other terms, the linear term and the quadratic term and the cubic term, just disappeared, and only that leading term dominated. Eventually, the function looked exactly like x to the fourth, right? It didn't even look like anything else. It just looked like the leading term only, right? So the leading term is the dominant term of a polynomial. If we're taking a limit as x approaches plus or minus infinity, it's the only one that really matters. And so we can just forget about those if we're taking this limit, only because we're taking the limit though, right? Let me ask you this. What's the limit of 2x plus 5 as x approaches infinity? What's the limit of 2x plus 5 as x approaches infinity? What is it? It's infinity, isn't it? It's going to get infinitely big, right? What's the limit of 2x without the 5 as x approaches infinity? So who cares? It's the same thing, right? We don't need that plus 5 on there. It doesn't really contribute anything, okay? So we can just get rid of those if we're taking the limit. Now, is 2x plus 5 over 3x squared plus 1 equal to 2x over 3x squared? It's not, but their limits are equal. They both go to infinity, okay? So could we have reasoned this out without doing any of this fancy algebra? If I let x approach positive infinity, let's just take the positive case. The top of the function is going to infinity, right? 2x is going to infinity. 2x plus 5 is going to infinity. 3x squared plus 1 is also going to infinity. Which one is going to infinity faster? The squared one, isn't it? The bottom one is. How much faster? Well, infinitely faster, right? Because it's infinity squared. And so do you see how that wins? Even though the top one is going to infinity, the bottom one is going to infinity infinitely faster. And so the bottom one wins by infinity, right? And so we could have said because the bottom is a bigger power function than the top, it's going to more aggressively go to infinity, which drives the whole fraction to 0. Okay. Now, would that do for an answer on an AP test? Probably not, because that's not really rigorous algebra. But conceptually, that's what's going on, isn't it? Right? Okay. Let's look at another example. How about one like this? Anyone care to make a guess what the limit's going to be? What's it going to be? No. Uh-uh. Mm-hmm. What do you think? What's that limit going to be? It's 2/3. Yeah. How come? Anybody else want to explain why it's 2/3? What do you think?
Can we like say how?
Yeah.
You just get rid of the 5 and 1 because those are irrelevant, and then you just
Yeah. Yeah, we don't even really have to. We could factor out an x squared from the top and the bottom like we did. We could easily do that, right? But we really don't need to. We could instead be really tricky about this and just say this is equal to the limit of the leading terms, ratio of the leading terms, 2x squared over 3x squared as x approaches plus or minus infinity. Well, look, the x squareds cancel. So that's 2/3 and we're done. Okay. Okay, how about this example? Now, oh, by the way, let's go back. I want to go back to these last two for a second. So we left one issue maybe a little bit unresolved. So we got the limit of this function as x approaches infinity or negative infinity is 0. So what does that tell us about the existence of a horizontal asymptote? If the limit of this rational function as x approaches plus or minus infinity is 0, what is the equation of the horizontal asymptote? Y equals 0, right? If the limit is equal to 0, then that's telling me that y equals 0 is the horizontal asymptote as x approaches infinity or as x approaches negative infinity. Notice we have a shared horizontal asymptote. And let's just look at how about if we attach a graph of this? That might be helpful to the notes here. You guys ever go back and look at these notes? Okay, good. Good. So this is worth the hassle then to attach these graphs. Okay, so if we're graphing the function 2x plus 5, let's just make this f of x equals 2x plus 5 divided by 3x squared plus 1. And sure enough, look what we get for our graph. We pretty clearly have a horizontal asymptote at y equals 1, don't we? Let's put that in there. Oops, y equals 0, not 1. What am I saying? 0. Okay. Okay, what about this next one? If the limit of this function as x approaches plus or minus infinity is 2/3, what's my horizontal asymptote? Y equals 2/3. Okay, let's prove it. If I go back and change the function here to 2x squared plus 5 over 3x squared plus 1. Now look what that does to the graph. Now I need to change that y-intercept to y equals 2, or that horizontal asymptote, and we can see it sticks to the function. Okay. Okay. Make sense? Okay. How about this one? What's the horizontal asymptote going to be there? Is there going to be a horizontal? This is equal to what limit? Two x cubed over 3x squared, right? Which is equal to the limit of 2x over 3 as x approaches plus or minus infinity. Everybody agree? If I cancel x squareds? Okay, well, that doesn't look like a horizontal asymptote, does it? I don't get a constant there, right? In fact, we could say on this one, the limit of this function as x approaches positive infinity is going to be what? If I plug in a positive infinity there, what am I going to get for my answer? Positive infinity. Agreed? Okay. The limit of that whole thing as x approaches negative infinity is going to be what? Negative infinity. So if I were going to graph this one, what's that tell me? Well, it tells me nothing about what's going on in the middle, but it tells me to the right, it's going up to infinity, and to the left, it's going down to infinity, right? Okay, but there are no horizontal asymptotes. It is interesting, though, that if I just look at the ratio of the leading coefficients, it does tell me what kind of infinity I'm approaching to the left and the right. Anybody see that? And if I were to graph this guy, look what happens. I'll even tell you that they're going to be linear. It's going to go to infinity linearly, and we'll talk more about that later. But so 2x cubed plus 5 over 3x squared plus 1, and sure enough, look what you get. Kind of behavior we predicted. So those three examples we just looked at were actually chosen pretty specifically. What's that tell us? Well, it tells us that we have these guidelines for finding the limits of a rational function as we approach plus or minus infinity that allow us to answer the question just by inspection. We don't have to do any work. If we go back to that first example, we could generalize that, right? Anytime, wouldn't you agree, anytime the degree of the bottom polynomial is higher than the degree of the top polynomial, doesn't that always mean the limit's going to go to 0? Right? Give me thumbs on that. Does that make sense? Okay, so then that gives us guideline number 1. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0, which means we end up with the horizontal asymptote y equals 0, right? Okay, what about the second example we looked at? If the ratio, if the degree of the top and the bottom is the same, then look, we just got the ratio of the leading coefficients was the 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 limit of the function, right? So therefore, that gave us our horizontal asymptote. So there's guideline number 2. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. And that tells us our horizontal asymptote. Okay, y was 2/3. And then finally, the last example we looked at, if the degree of the numerator is less than the degree of the denominator, then, oops, sorry. If the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. It's infinite. But we could tell what the sign of the infinity was on the left and the right. So we actually know on a broad scale, is the function climbing to infinity or dropping to negative infinity at both tails, okay, which is helpful. All right. The first two go together, right? 1 and 2, they give us horizontal asymptotes. We had horizontal asymptotes in the first two cases. Third case, there was no horizontal asymptote. And notice that for rational functions, they always share a single horizontal asymptote as x approaches plus or minus infinity. Okay, and the limits as x approaches plus or minus infinity of both ends, right, the left or the right, are either going to be both finite or they're both going to be infinite. Okay, give me 1 to 5. Does that all make sense? Okay.